Hey guys, you're watching Python tutorial videos on my YouTube channel Python for Microscopists. In the last tutorial, we talked about the basics of Generative Adversarial Networks, or GANs. And in this tutorial, let's actually go ahead and implement it in Python using Keras. Okay, and we're going to do both the training part and also the testing part. Now, just to give a quick, again, summary of what we talked about in the last tutorial, the term generative means we are generating something. In this example, generates data or generates images. Yeah, image is a form of data. Adversarial means the generator and discriminator are each competing to win, where the generator is trying to create fake data that looks realistic, and the discriminator is trying to catch this fake data. Okay, and as we train, they both get better at their respective jobs. Like generator gets better at faking the data and discriminator gets better at discriminating. And there comes a point where the generator is so good at faking this realistic looking data, we're going to take that as our model and then generate further images. And those images can be used for other applications, which I talked about in the last tutorial. Okay, so again, just a quick summary. So what we have to implement is a way of creating random seeds, right? Random noise, that's easy. Defining a generator network, okay? This is not easy, but we are going to copy something that already exists from somewhere else, which I already did. Read a whole bunch of papers, look at a lot of code on GitHub or wherever people published it, and take something that actually works. And most of the code that you see are probably some incarnation of the data of the architecture from the original paper or some other papers that got published in this field. Okay, no one like me at least is sitting and putting together these things because I'm not smart enough to do that. Okay, I'm smart enough to take something and then customize it for my task, but not smart enough to put together a network, and not many people are good at that anyway. Okay, continuing, we also need to find a way of actually getting real images and then supplying them both to the discriminator network that we are going to define. And of course, the discriminator will at least classify this as real and fake, and then we have to get our discriminator loss, generator loss, and retrain this network. So that's the plan. Now, before jumping in, a couple of housekeeping things. First of all, in my past tutorials, in my past videos, I should have talked about what version of Python and what version of something else I was using, because that really that's very important for you to repeat, this experiment. So I just restarted the kernel, so you can see I'm using Python 3.5.5. I know Python 3.7 is out there, but I have a GPU, an older GPU called NVIDIA Quadro K5000. And it took me quite a few days to figure out how to get my GPU, for TensorFlow, GPU ready for TensorFlow. So I looked at, okay, what version of CUDA drivers do I have, and all those drivers and all that stuff. So I don't want to make this a video about my grievances, on how I got this GPU ready, but again, there's a lot of material out there that you can follow to get that done. So continuing, Python 3.5.5, what else do you need to know? Let's actually import Keras, so you can see the version of Keras that I'm using, and also the TensorFlow. I totally don't remember what they are, so let's go ahead and do that. Version, so the version of Keras I'm using is 2.0.8, and let's also import TensorFlow STF and TF version, and I'm using TensorFlow 1.4. I believe 2.0 is out. I know that 2.0 is out, but I'm using the older version because, again, for me to use this GPU, I have to have this version of TensorFlow, that version of Keras, and so on. Okay, now that we talked about this, a couple more things. So we are, so here you see I'm defining my image as 28 by 28 by 1. That's because I plan on working on MNIST dataset. And you're probably aware of what MNIST dataset is. If not, well, let's go ahead and cover that. I thought of actually Control C. Let me just show you what MNIST is. So first of all, you can download this MNIST dataset as part of keras.datasets. Okay. If not MNIST dataset, you can actually download it and you can leave it on your hard drive locally and then use that. Either way, it's okay. So first, let's go ahead and download that. Okay, there you go. I have it. And now let's unpack it. So there are two in there that we need to unpack. And let's load. And here, let me open my tuple for X. Okay, so there is X and Y. Okay, so I opened X and you see my X is 60,000, which means we have 60,000 images of handwritten digits. And each image is 28 by 28 pixels. In fact, if I open this, you can see image number 0, right? I mean, down here, my index is 0. Image number 0, it kind of looks like 5. Someone writing a very bad way of writing 5. Okay, of course these are handwriting, so it is not pretty. So if I actually go to index 1, which is the second digit, it looks like it is 0. Again, this is a bit extended in this direction because you see the cell size is extended in this direction. But anyway, so this is 0, and if I keep going, what is the next number? It almost looks like 4. You see, I mean, it's stretched in this direction because of the window, but again, this looks like it's 4. And the next one is, it looks like, I don't know, maybe 1. But so let's just look at the first few. Okay, so again, 5, 0, 4. Okay, and the reason why I'm stressing on that is if you look at the other units here, you see 5, 0, 4. These are all the labels of these images. So these are, X is all the images. And the second variable here, or the second parameter here, is your ground truth, which is it number 5, 0, or 4? So this is the data set we're going to work with. Okay. Now, let's go ahead and continue. First, let me explain at a very high level. We are building a generator, and then we are building a discriminator. Again, going back, we are building a generator network. We are building a discriminator network, and then we are going to train these two networks first on real data. You see, we are loading MNIST data right there. And then on fake data, we are going to generate a whole bunch of fake data by using our generator. Okay. And then we are going to save the images after so many epochs so we can see how the model evolves as a function of time. Okay, and then other parameters, hyperparameters, like defining your optimizers and so on. And the combined, again, we'll get to what the combined is. Combined is when you attach this discriminator and generator together. Okay, so that's at a high level. Now let's go through this line by line. I'll share this document as part of my GitHub repo. Again, the link will be in the description. So you can go through this, and I added as much text as possible so you can read this yourself. And if you find my video, me talking boring, you can always read this text. Okay. So let's import. Again, I don't want to explain what this is. This part is basically importing our MNIST data set, importing the required layers like our input layer, dense layer, and reshaping and flattening and batch normalization, all of these. Okay, this is very standard, as you probably know. Now here I'm defining my image rows as 28, columns as 28. And again, these images are all grayscale, but I would like to add a channel to my image shape so it becomes X, Y, and number of channels. So for example, if you want to work with color RGB images, then you can change the channels to 3. Okay. Now build the generator. And again, if you give, what this does is the input is noise. Okay, the input to this generator is noise. I define the noise to be a vector of size 100, right? 100 by 1 in this case. So it's one dimension, 1D array of size 100. So this is the input that goes into this sequential model that we just defined. And this is very, again, this should not be new to you if you watched my unit tutorials or one of the previous deep learning tutorials. So we are just, to this model, we are actually adding a dense layer. You see the dimensions 256, and then we are using leaky ReLU. Again, I talked about this, and alpha is the hyperparameter. Why 0.2? Don't ask me. I'm just copying this from the published paper. Again, this is where the sensitivity of hyperparameter really is very important. And momentum is not that big of a hyperparameter. Momentum is just how fast it actually trains. So I'm going to use this, leave this as 0.8. So it's basically 3 dense layers, going from 256 to 512 to 1024, okay? And batch normalization between each step. Now, and the final layer is, again, my activation is our tan H activation. And finally, I'm reshaping this and the noise and the image, right? So this is what the function here, my generator function, returns, okay? And the noise is, again, this, you can call this a latent vector if you want. Some people call it latent vector, but noise is basically the random input vector. I should show you this vector, okay, that goes into the generator framework. And this image, I should have actually labeled this as generated image or fake image. That image is this image, the fake image that goes into the discriminator network. So this takes in a one-dimensional array as input, yeah, of 100 values, right? One-dimensional array, and it generates a two-dimensional image of 28 by 28 by 1. Okay, so that is what this is returning. Now, if you look at the discriminator, okay, again, the input is an image for the discriminator. Remember, the discriminator is nothing but just like a binary classifier. It just says either it is a real image or a fake image, 0 or 1, okay? So given an input image, it outputs the likelihood of the image being real, okay? So again, I have only 3 layers over there, dense, 3 dense layers, and then the activation is sigmoid here. And again, what it returns is the image that we supply, yeah? And the validity, you can call it score, or is it true or false, whatever it is. The validity is the value that it gives, saying that, okay, is this a real image or a fake image? Okay, it's basically the probability. So these are the 2 layers. Now moving down, I'm now defining the training part of it, okay? And the input parameters are number of epochs, the batch size, and save interval. How often do you want to save? Let's actually change this to 500 if I want to save this, but we can give this input later anyhow. Okay, these are just the default values, right? Now, first, we have to load the data, real data, okay? So this part, I'm defining this part, real images. I'm loading this real images here, okay? And I only care about xtrain. These are the real images that we are trying to import, okay? Again, xtrain, something else, ytrain, something else, right? Again, we looked at that data set here. So all we're trying to load is, again, just these 2 parts, this part, okay? All 60,000 of it, just this part. So that's what that is signifying there. And now, because these are all, again, you see, these are all unsigned integers, okay? Let's actually convert them into, rescale them into floating point, and then rescale them to -1 to 1. You can do 0 to 1, okay? Floating point numbers. I'm doing -1 to 1. And the way we do that is, again, -127.5 divided by 127.5. Again, you can go from 0 to 255 if you want, between 0 to 1. So this step is very straightforward. Again, if any of this is confusing to you, just like I did here, load the data set, extract this, run this single line, and see how the output looks like. So this is how you learn, okay? And then now we are expanding the dimensions. All I'm doing is adding an extra axis. Again, this is, otherwise the shape would be 28 by 28, right? These are grayscale images. Now I am adding extra channel to make it 28 by 28 by 1. Okay, that's all this is. And now I define half of this batch is batch size divided by 2. Okay, that's because I want half of it actually going into the discriminator. Again, let's go back. Half of these images go into discriminator and half of the real images go into discriminator. Okay, so I want to mix half and half. That's why I just do batch is half of the batch size. Okay, so meaning in this example, if I have batch size of 128, 64 would be the half batch. Okay, now if we say, okay, 1000 epochs, now for each epoch, okay, train this discriminator first. Again, we train the discriminator first, and then the generator, and then the discriminator, and then the generator. While we are training the discriminator, our generator does nothing, and while we are training the generator, the discriminator does nothing. Okay, it just sits there. So let's start by training the discriminator here. And how do we train? So select a random half batch of real images. So we are taking these real images, right? And then we are taking a random half batch of these images. And so that's what I'm calling IMGS. Okay. And here I'm actually creating something called noise. Okay. And this is a Gaussian noise, normally distributed noise between and the half batch and 100. Again, anytime you have any question, what the heck does it do? All you got to do is just come here and then run line by line if you want. Let's say my half batch is 64. Okay, so what does that mean when you run that? Well, you have to import numpy as np. Oh, there you go. And now you can see my noise is it generated 64 of 100 dimension vectors. That's all it is. So I have 64 of these. You see, 0 to 63, and each of this is 100. So if I go in this direction, we should have 100 of these. Okay, so that's all this is doing. So it's actually generating 100 different noise values because we would like to input 100 of these into the generator. Okay, and the generator is predicting on all of these 100. In other words, 100 images are 100 random numbers are going in. 100 of these random numbers are going in. And then what's coming out is 100 of these images. That's exactly what this line is doing. Okay, generate images is generator.predict. Okay, so we already have our generator up there. Okay, so don't want to dwell on little trivial topics, but sometimes these make such a difference, right? Not understanding a little topic makes such a huge difference in us implementing this code. Okay, so don't mind me explaining these little things. Okay, so now let's train the discriminator. I'm going to train it, okay, on images. Remember, these images are the real images. These are not fake, right? So these images that we are getting out of our MNIST dataset directly. So I'm going to train on these images, and then I'm going to get this loss as real loss, okay? And then very similar, I'm going to do that on generated images, yeah? Generated images, and then I'm going to take this as fake. Okay, so half of this, half of that, we are going to take and train the discriminator, and we'll get two loss values, one for real, one for fake. Again, as you can see in this, you get for discriminator, you get I showed this as single loss. Well, how do you get a single loss? You just average real and fake, meaning I'm just adding those two and dividing by half, right? Or dividing by 2. So my discriminator loss that I'm keeping track of is an average of real and fake images, the loss that we are coming between these two. Okay, our discriminator is trained. We are done. After training the discriminator in this epoch, right? Within this epoch, go down and train the generator. And don't do anything to the discriminator. So to do that, for generator, I'm going to generate noise again, okay? Very similar to the definition that we have done earlier. And then I'm gonna generate corresponding truth values. Again, the Y value here is the image probability, right? Typically. Now, this array generates an array of all ones, okay? Again, if you wonder what this is, I'm pretty sure most of you know, and you're probably getting frustrated because I'm explaining little details, but believe me, there are people who need help, and this is for them. Okay, so when we do that, the valid Y, it's actually generating a whole bunch of ones, but in the column format, not in the row format, meaning we have to reshape it, but that's okay. Or does it not matter? But let me go through the code. It's so anyway, so this is all ones. Actually, in this case, we don't reshape yet. We will at some point. So these are all ones. Now, why am I calling all my fake images to be true? In a way, this is basically, this step is very important for this GAN. Okay, so let me dwell a bit of time on this. So I'm generating fake. I'm going to generate fake images here. Yeah, train on batch, yeah, providing the noise, and I'm calling them that this is real image. So this is my way of fooling the discriminator that a fake image is real. So I'm challenging the discriminator, hey, this is real, take it. And then the discriminator takes this and it's like, no, this is not real. Yeah. And then gives it back. And then this is how this entire training thing goes along. I hope it's making sense to you. So the reason we, again, created this, this parameter with all ones is to say that, okay, now look at the generator loss and then combined.train on batch. What does combined mean? If I go down again, combined is the model that we are actually generating using an input array, like Z is our input shape, some array, and then valid. The valid is, again, the probability. Sorry for the name. It's actually probability over there. Okay. Again, let's go back. Let me repeat this. Don't want to confuse you. Read the text if you think it's confusing. Okay. Now, so where are we? So right now, so we are about to train the generator. Again, the way we train the generator is via combined. Okay. In the combined method, we are combining the arc network for the generator and the discriminator, but then we're not training the discriminator part. We are only going to train the generator part. Okay. So again, it probably makes sense once I go down, but that's exactly what we're doing here. Okay. Train on that by fooling that a noise or a fake image is a real image because we are supplying a Y value of 1, which is true. Okay. Now I'm going to print, okay, as the epoch goes along, I'm going to print the loss for discriminator, the accuracy. For discriminator, we'll track the accuracy there and the generator loss, okay? And then the epoch number and all that stuff, okay? This is just a print statement that actually is printing all the values that we are keeping track of. And if epoch, after every so many epochs, okay, which is after so many epochs, we are going to actually save these images. But all this is saying is, okay, just save these images, and it runs this this part of the code, right? So once a certain number of epochs are reached, we are going to actually, in this example, what are we doing? Like printing 5 by 5 grid of images, okay? And we are saving it. So basically we are generating 25 random images we are picking 25 images out of these predicted ones, and we are actually printing them. So we'll see a grid of 25 by 25 after so many epochs. And this is up to us, right? After how many epochs we need to print this. Okay, so that's quite a bit. I just want to scroll up here to show you the save interval. So in this example, after every 500 epochs, just go ahead and save this. Okay, save these images. Now, let's actually go down to the main part of the code. Okay, up to this point, these are all individual functions. Okay, so now we are into the main part. Okay, so let's use optimizer as Adam. Because we are using this optimizer multiple times, I just defined it up here. Okay, there is no other special reason. And for discriminator, let's actually use binary cross entropy, because remember, discriminator is a binary discriminator. It's a binary classifier. So binary cross entropy works much better than mean squared error or any other type of loss function for this type of problem. So that's why we are using binary cross entropy loss. Okay, and let's keep track of accuracy as the metric that we need to keep track of. And that's it. So all we are doing is compiling the discriminator right here. Okay, and the next part is generator. Okay, build the generator, and again we are compiling this generator using binary cross entropy, and optimizer is, again, we are using the same Adam optimizer. Going down, what else do we have? Okay, so my Z is the input shape. Again, this is the input parameter that actually goes into my model. Okay, so Z is this vector that we are talking about of size 100. Okay, so that's my input of shape, and then my image, or the fake image, is the one that got generated using this as my input. Okay, that's what this is. Why am I doing this? Because I would like to go down to combined in a second, but let me explain this discriminator.trainable equals to false. This is very, very important and counterintuitive also. We said like, okay, discriminator, what does that mean? We are not training discriminator? No, we are training discriminator up here anyway, okay? And then we are into the generator part, and down here, okay, before actually we train our generator, I want to keep my discriminator as non-trainable while I'm doing my generator. That's what this generator discriminator.trainable equals to false means. Again, while discriminator is being trained, generator does nothing. While generator is being trained, discriminator should not be trained. Because we are using a combined model where we have combined discriminator and generator, we have to mention that discriminator is not trainable. That's what this line is, okay? And then my probability, or the valid, equals to discriminator, okay, of this image. So we are now running this discriminator. So we built the discriminator here, right? Built the discriminator here, and then down here, again, I recommend you going through this line by line. You see how we just built discriminator. We are calling that function here, and then we are compiling it. Down here, I'm just basically running that by supplying my input as the image that actually is coming out of my generator here. Okay, so this is this generator part, and so now that I have my valid, which is my probability here, I'm going to go ahead and run this combined model with this as these as our inputs, okay? And again, Z is our input into, I paused there for a second because I felt the need to explain this one more time. Again, I know this is going to be a long video, but I hope you pay attention here. Generator, what goes in as the input? A vector of size 100, which is what we are calling noise. This is basically random noise that we are supplying. What comes out of this is a fake image. So generator, noise input, fake image output. Discriminator, image input, and the validity score as output, or the probability, or is this a fake or real image as output. Now when we combine them down here, we are combining them, yeah? So the input is the vector, because our generator input is the vector. The output is this valid or not valid? The output of the discriminator, okay? So that's because we combined these two models down here. This is how, again, please go through this. If this doesn't make sense, watch another video. I don't want you to be confused, okay? But this can be a confusing topic initially. Okay, so now that you do that, we just need to train it on how many ever epochs, how much ever our batch size is, and save interval, how often do you want to save, okay? So let's actually do, because I have a system with one GPU that's 4 GB RAM, it's not super duper GPU, but still better than CPU. Let's actually train it for 100 epochs and save it for every 20 or 10 actually, okay? And then so we can see some images. I've already trained this on 100,000 epochs, so I can show you the final result. And eventually I would like to save the generator, model, and here it is, generator model H5. Okay, this is the file I'm saving it to. Okay, let's go ahead and run this. And on the right hand side, you can see the progress. Okay, so it says no such file images /mnest. So what that basically means is when it is running, oh, sorry about this. Let me actually import. I was experimenting with this. That's why I left the title to be experimenting, or my misspelling of experimenting. It's okay. So let's run this because I was running a different file. So everything's same. Of course, it's exactly the same file, epochs 10. Let's change the epochs to 100 and change this to every 10 and run this. And now I hope it should run fine. That's because previously it didn't find the folder images. That's all it was. Okay, so there is our print statement here. This print statement, or discriminator loss, accuracy, And this accuracy of 100, I don't think we should even print this accuracy anyway. But let me go into this images that it actually just output here, and let's look at it. So this is after 0 epochs. This is after 10, after 20, and so on. It's still after 90 or 100 random noise, nothing there. So let me just show you my 100K epochs, and here is 0. And here is after 2000, I mean, yeah, up there, 2000, 4000, 6000, and so on. And as you see, again, these images are completely fake. No one wrote this. The GAN here is writing these, creating these fake images. That's all. Okay. So as you can see, as the number of epochs improved, so at about 50,000 epochs, I actually got like something that looks very realistic. There you go. So as I keep going, like all the way to 90,000, 92, 94, 96, now it almost looks very realistic over there. Yeah, some it can just definitely improve upon, but that still looks like 8. So this is how you can actually train your generator. Just to finish this off, let me just show you how you can predict just by using the saved model. Okay, here I have the saved model after 100,000 epochs, and this is something that people share when they publish papers, and that you can use to actually create your own images. So here, let's just do a single image. So I'm importing the required libraries again. So all we need to do is load the model, okay, generator model right there. And now we need to supply a random vector, right? Remember, this is the input. And then our output would be an image. So I supply a vector. Again, I'm generating something of size 100. Again, that needs to be reshaped, because if you just do this, then the vector is in the wrong direction. So anyway, so I'm reshaping it here. And now I'm generating an image, which is just model.predict. We know this, right? And the input value is vector. So it's taking this model and taking this input vector, and it actually predicts it. And now I'm just doing pyplot.imshow to show this image. So let's go ahead and run it. There you go. It shows some image. Let's run this one more time. It should show something else. Right, looks like number 3. These are all, again, the fake images that we are generating. If you would like to do multiple images, so instead of just 100, instead of one vector, we just define multiple vectors for multiple images. That's pretty much it. And I'll share this file also. But anyway, so the way I'm doing it is I called it, again, latent points. These are vectors. And dimensions and number of samples. And dimensions, again, I think I got this code from one of the blogs I was reading. I should keep better track of these blocks so I can properly acknowledge them. But anyway, and then I'm just saving these plots. Okay. And in this example, looks like we have 16 images that, or 16 of these samples, again, latent points that we are generating. And so I'm actually plotting a 4x4 grid here. If you generate 25, plot it as 5x5 grid. Okay, so let's go ahead and run this to end this video. There you go. So our 4x4 grid of realistic looking images. So now I can use this model to generate MNIST numbers. So I hope you learned something from this video. I know it's a lot, it's quite a bit, it's a very long video, but I tried breaking this. In fact, this is the 4th time I'm recording this video, because I tried breaking this into chunks of 10-minute videos, but you will lose the continuity. I thought this was the best way to communicate what I have in my mind. So hopefully it comes off as very effective. Anyway, again, thank you very much for watching this tutorial, and please subscribe to this channel. Like I said, it keeps me encouraged to create more such content. Thank you.